check this out. We've got something really fun today. This is so amazing. Oh man, again?
5.4, solving trigonometric problems. We'll start off by reviewing how do we solve this trigonometric equation given this domain restriction. So we need to isolate x here. Let's add 3 on both sides of the equation. We have 4 sine squared x is equal to 3. Let's divide by 4 on both sides of the equation. So we got sine squared x equals 3 over 4. Then we'll take the square root of both sides. So on this side, we'll get plus or minus sine x. And on this side, root 3 over 2. And then I'm going to push the plus or minus over to the other side. And we get sine x equals root 3 over 2 plus or minus. And if we remember our unit circle, if it's plus or minus, that means that it could be in any quadrant. And sine's ratio root 3 over 2 is when there's a reference angle of 60 degrees. So 60 degrees, 60 degrees, 60, and 60. So we're allowed to go one full rotation in the positive direction. That would be like this way. So our reference angle's 60 degrees here, and here as well, and here, and here. So our x is equal to, first angle here we hit is 60 degrees, same as our reference angle. Then we hit 120, and then 240, and 300. Those are the 4 solutions to this equation. Electrical current from a wall outlet in Canada is alternating current, which completes 60 cycles in 1 second. Now, alternating current is where the current is pushed and pulled, which changes direction. Direct current, like you'd get from a battery, is just a constant supply of energy. The voltage can be modeled with the function this, where t is time in seconds. What is the period? If you took physics, you may remember it's 1 over the frequency, but let's do it the math way. So our period is 2 pi divided by our b value, because 2 pi is our regular period, and then b is our horizontal stretch, and we're stretching this period here. So 2 pi divided by 120 pi is 1 over 60, and we're measuring our period in seconds. If you plug in a heat lamp that needs 110 volts to start up, how long will you have to wait until it's able to start? Well, we need 110 volts, and the voltage changes, and so we don't automatically have that. So we need to find the time where we have 110. Or when we first have 110. So we just need to solve this. Now I'll solve this graphically by putting this in y1 and this into y2. Let's just give a quick sketch of what we expect to see graphically. So we've got our y-axis here would be in volts, measured in volts, and this would be time measured in seconds. We have a sine function here with no reflections. That means it starts at its midline going up. The midline is the d value, and in this case the d value is 0. So we'll be starting here and going up. Now our amplitude is how far we go up, so it's 120. So this here will be, the maximum will be 120. And this one down here will be negative 120. Now, the period is 1 over 60, so we're going to have to change our x min and max to be very small, and our y min and max to be very large.
The first thing we need to do is make sure our calculator is in radian mode. So the question is not in degrees, so by default then it's in radians. Now I'm going to put the left side of the equation into y1, so 110, And then in y2, I'll put 120 sine 120 pi t, or x in this case. Now I'm going to change my window so that I only see one period, or one cycle. So I need x minimum to be 0 and x maximum to be 1 over 60. And I'll just put my x scale as 1. The y minimum I could put as negative 120, and the y maximum positive 120. And a y scale of 10. Let's look at the graph. That straight line is the 110, and this curved line is our sine function. And we're looking for this point right here, the first intersection. So I'll go second, calculate, number 5, the intersect. And we need to move Blinky closest to that intersection, and then hit enter 3 times. So that we see our first intersection is 0.003. So from the graph, we have that t is equal to 0.003 seconds. So we'd have to wait that long before our heat lamp started up. Now, solving graphically can be a great way to get the question done quickly, especially when it doesn't say do it algebraically, but you really need to know both ways. Example 3, we want to solve this equation here. Now, it doesn't say algebraically, so the first way we'll do it is graphically. And if we solve graphically, we need to be in radian mode. We need to put this as our minimum x, this is our maximum x. And we see that sine has no vertical stretch, so y minimum would be -1, y maximum would be 1. And graph it, and we would get that the only solution here is x equals 4 over 3. And here's what a graph looks like. And so our only solution is right there. But let's say we wanted to do this question algebraically. Should be easy enough since this is a value off the unit circle that we know. So let's take the sine inverse of both sides and look at our unit circle for where is sine's ratio, positive 0.5. On the unit circle, it means that if sine's ratio is positive, we're in quadrant 1 or quadrant 2. We have a reference angle of pi over 6, or 30 degrees. So this one would be pi over 6, and this, in standard position, would be 5 pi over 6. Let's try pi over 6 first. So sine inverse of 0.5 is pi over 6. Do some algebra and solve for x. So multiply and divide here, multiply and divide here. Pi's cancel, 4's cancel on this side, and x minus 6 is equal to 2/3. Add 6 on both sides, and I'll just write this using a common denominator, so plus 18 over 3, that's 6. So if we add that, that is 20 over 3. Now that is about 6.66. This is too big. This domain restriction here has a maximum of 2 pi, which is about 6.28. So this is too big. It's not going to fit in the domain restriction. Now let's try the other angle here, 5 pi over 6. So same left side here, except the right side, instead of pi over 6, I'm going to solve it for 5 pi over 6. Do the same algebra. Here, multiply by 4 on both sides, divide by pi on both sides, and we get x minus 6 is equal to 10 over 3. Now we need to add 6 on both sides, so add 6, and on this side I'm not going to write 6, I'll write 18 over 3, because I know I need a common denominator just like before. This equals 10 10 over 3 plus 18 over 3 is 28 thirds. Now, this is way too big. So the first one is too big. This is way too big. So you see which direction we're going. We're going, as we go counterclockwise here, we're going to get larger and larger values. So option 1 here is to take a negative angle instead. If these positive angles were too big, take a negative angle. So option 1, take a smaller or negative angle. So this angle right here in standard position is negative 7 pi over 6. So let's try this whole process again with negative 7 pi over 6. So that would be this angle here, negative 7 pi over 6. Now do the same algebra. So multiply by 4, divide by pi. Multiply by 4, divide by pi. Cancels all that stuff out. X minus 6 is equal to, pi's cancel, 2's cancel, so negative 14 over 3. And we'll just add the 6 on both sides. So on this side I'll add 6. On this side I'll add 6, which is 18 over 3. And then 18 minus 14 is 4 over 3. And we actually have the solution that we found earlier graphically. Now, if that smaller angle worked, though, what about the next smaller angle? If we were doing this blind, we didn't know that there was only one solution, we might be looking for the next smallest one. So if we were doing it algebraically, that's what we'd be doing. The next smallest angle here would be negative 11 pi over 6. So let's try that. Try next negative angle, negative 11 pi over 6. So same deal, we got pi over 4, x minus 6 is equal to negative 11 pi over 6. Same algebra. Pi's cancel, 4's cancel, and this would be negative 22 over 3. Add 6, and we get negative 4 over 3. And this is too small for our domain restriction because our domain restriction started at 0 here. So we can't have any negative x values. So in this option 1, we proved that there's only one solution. These two are too big. This one is just right. And this one was too small. So we're good. This isn't the only way to do it, though. So option 2 is subtracting the period. If we have some solutions that are just too large, so I'll just draw a hypothetical sinusoidal curve here. If we have a solution, two solutions that are too large, if we just subtract the period, we'll go find the solution before. So this one, and then we subtract the period, and we'll find that one. So let's try that. First, we need to find the period. And the period is 2 pi divided by b. And in this case, it's 2 pi divided by pi over 4. And that equals 8. So our period is 8. So 20 over 3 minus 8 is 20 over 3 minus 24 over 3. And that's negative 4 over 3. And this one's too small. It's the one we found second here. Let's try the other one. 28 over 3 minus 8. And this one works just fine. This is the solution, the 4 over 3. We want to solve this equation in radians. There's no domain restriction, so we'll have to write our answers in general form. First thing I will do is divide both sides by 8 so I can get my cos function by itself. Next I'll take the inverse cos of both sides And using a unit circle, we can see where these happen. If cos's ratio is positive, that means we're in quadrant 1 and quadrant 4. So if I take the cos inverse of 3/8, I get 1.186, or I get a reference angle here of 1.186. Also here, same reference angle. Now if I actually wanted to find that right angle, though, I could just call it negative 1.186, and so that's what I'm going to do. I'm going to call the angle in quadrant 1 positive, and the angle in quadrant 4 negative. And then I'll do some algebra and solve for x. So x is equal to plus or minus 1.186 plus 5, all divided by 2. This gives us two solutions. We've got 3.093 and 1.907. And we want to write these in general form. So we need the period. Don't just add 2 pi each time. So 1.7 plus. And the period would be 2 pi divided by the b value. In this case, the b value is just 2. So our period is just pi. So we got our first angle here, 1.907 plus pi, any n number of times. And our second angle here, 3.093 plus pi, any n number of times. A student was swinging on a swing and decided that it would be a lot more fun if he had the equation of his height off the ground as a function of time. His maximum height is 2.2, and his minimum, down at the bottom here, is 0.4 meters. It takes him 1.2 seconds to travel from one side to the other. And assume that he starts at his maximum height at time 0. And he's going to be swinging at a constant rate. So we just need to find our A, B, C, and D values. So A is the amplitude, and that would be max minus the min divided by 2. So our maximum is 2.2, our minimum is 0.4, and subtract those and divide by 2. So this would be 1.8 divided by 2, and that would be 0.9. Our B value is 2 pi divided by the period. So in this case, from top to top, or maximum height to maximum height, would be 1.2 seconds. So the period is actually given to us in the question. And then we could just make this look a little bit better. 1.2 is, say, 5 over 6. And then we could simplify the 2 here. So this could equal 5 pi over 3. Our C value is our horizontal shift, and we want the graph to start at its maximum. If we were going to use sine, then we'd need to shift the graph over because sine starts at the midline. But if it's starting at the maximum, we should probably just use cos, because cos already starts at its maximum. So we won't need a C value here. D is the midline, and it's max plus the minimum divided by 2. This would be 2.2 plus 0.4 divided by 2. So 2.6 divided by 2, 1.3. And now we're ready to make our equation. So this is the height, our variable's time. First is our A value, 0.9. Next is cos, because that's the one we're going to use. Then our B value, 5 pi over 3. T It's our variable. No c value, so we'll just close the brackets here. And our midline, or d value, is 1.3. And there's an equation. We'll model his height. This was part of Trigonometry 4, graphing and analyzing the trigonometric functions sine, cosine, and tangent to solve problems. Here's some questions. Give them a try. See if you know what you're doing.